Thank you. Thank you so much. Hello, everyone. Welcome. And good morning, good afternoon, good night, depending upon where you are. Thank you so very much for joining us today for this live stream. My name is Reza, and I'm the stream owner on the Quantum Science and Technology on Aggregate Intellectual. And I'm the CTO and co-founder of QSpice Labs, a quantum technology company here in Canada. Today, we have the honor to have Dr. Mehdi Namazi from Qunnect here with us. He's going to tell us about the real-world quantum communication, one module at a time. It's a very, very exciting topic these days. We are hearing about quantum communication and all the great promises that they're bringing everywhere. So I'm very excited to learn more about quantum communication and where it stands as today from the very expert Dr. Namazi about it. If you have any questions during what he talks about what he's talking, and we are more than happy to answer those at the end. Please type them on our YouTube channel. We will get to those questions at the end. Just a very brief bio from what we know about Dr. Namazi. He received his PhD in physics from Stony Brook University in 2018 under the supervision of Professor Eden Figura. He's the co-founder and CSO of Qunnect. Since 2017, Qunnect focuses on engineering novel quantum memories and sources that will enable future information networks and quantum computing. The R&D develops scalable quantum memories using photons to communicate and atom nodes to store and process quantum information. They also develop quantum entangled photon source and randomly polarized photon source for hypersecure networks. Mehdi has a deep expertise in developing quantum communication technologies. His research accomplishments include experimental realization of the first room temperature quantum memory, demonstration of secure information storage using combination of quantum memory and quantum key distribution protocols. Thank you so much, Mehdi, for being here with us today. Thanks for your time. I will ask you a few questions, and we really appreciate if you can clarify and tell us more about these concepts before we get to your paper and your presentation. How does that sound to you?
Perfect. Awesome. Let's go.
Wonderful. Thank you very much. So when I was reading your paper, the concept of quantum information processing, it comes up a lot. Would you please tell us more about what is basically quantum information processing?
Of course. So first of all, thank you very much for the introduction. I'm very glad to be here. Quantum information processing is, or in quantum information science in general, is a concept that's been going around for the past several decades. Is that around the time we started understanding quantum physics, we realized that quantum particles, photons, atoms, they leverage from properties that we don't have in our classical day-to-day life. Things like superposition, that the particles can be on multiple different states at the same time, or quantum entanglement that creates a very unbreakable bound between them, correlation between them regardless of how far they are from each other. These properties are comes very handy, but we realized that we could use this in processing and transferring information in order to enhance how processing works compared to digital, for example, and how communication works. The quantum computing one is much more known. It's what we use all the time nowadays. The quantum computing is the one that, hey, let's use superposition and things like that in order to have more powerful computers that can do things much faster compared to a digital computer. When it gets to communication, it's more about if we do transfer information rather than using like classical optical pulses, if you go down to single photon level and encode our information on literally every single photon that is traveling in the fiber network, now we can leverage from advancements like moving towards unhackable quantum networks, make the network very, very much more secure than what digital communication can offer, and many other applications that I will talk. But yeah, this is briefly what the whole fuzz is about. Now we're getting in a more exciting time in which technologies is advanced enough that we can start like experimenting and showing some of those concepts similar to what Google, IBM, and other companies are doing.
That's great, great. Thank you very much, Mehdi. So it sounds like we should be worried about the advancements in quantum computing and what that can bring to the safety and security of our digital life. Is that how we should interpret your explanation of quantum information?
Well, not really. Yeah, what we should be worried about when it gets to cybersecurity is how, in long term, unsafe the digital communication is. The quantum is much more robust method of encoding and robust method of processing in general. So the problem is not coming from us moving towards quantum. The problem comes with us getting very used to processing everything digitally, and now missing out on like better methods pretty much.
I see. Okay, thank you so much. Next question is quantum communication. How is that different from, the communication that we all know and used to?
Well, the typical communication is usually, so the part that matters to me more is how we do encode the information. How do we encode the 0 1s to travel into a network? Right now, everything is pretty much either free space, like satellite-based, or fiber-based using telecom fibers. But using optical pulses is very, very common for sending your strings of 0s and 1s. These are optical pulses with billions and billions of photons in each pulse. Yeah. So the system is designed for being able to transfer this kind of optical pulses. Of course, you can have all the Wi-Fi and everything else, but the infrastructure itself. Now, the part we care about is that we reduce the number of photons in these pulses to bring it down to literally 1 or less photon per pulse, which will allow us to leverage from these properties of photons that we can now have 0, 1, but also 0, 1 at the same time in so many different dimensions, which gives us these abilities to securely transfer our secret codes without being worried about someone listening to it or things like that. So that's the biggest difference, is literally by bringing down everything to single particle or single photon, so we can have the quantum laws.
Okay, thank you very much. So it comes down basically to be able to leverage or use the advantage of quantum light versus classical light in transmitting and encoding the data.
Pretty much.
Very nice. Thank you very much. Okay, the other really interesting concept in your paper is about quantum memory. So would you mind telling us more about how quantum memory is different from, the classical memory that we all have in our digital life?
Sure. So when you start building like a whole new concept, because quantum science, information science is talking about making new computers or making new communication protocols, then you literally have to build every device that also existed. So equivalent of every digital device, you need the power source, for example, for a computer. You need the RAM, you need the hard drive, you need the processor. So everything that right now, for example, Google is doing or IBM is doing, it's not an actual quantum computer per se, it's a quantum processor. Yeah, it still needs its cache, it needs its RAM, it needs the source, eventually technologies that allows it to come together in form of a computer. Now you can literally take all those names and put a quantum at the beginning. So if you had memories in a digital computer, now you need a quantum memory. And everything again comes back to this concept that before, a normal memory is storing 0s 1 in terms of a magnetic field or like many electrons, things like that, coming pulses at 0s and 1s. But now we want to be able to store a single photon for a certain amount of time. But not only we want to be able to store this photon, we also want to be able to store the information that this photon is carrying in most cases in terms of, for example, polarization. And the quantum memory is capable of storing and successfully retrieving this polarization back after some microseconds or milliseconds with a high probability. The applications are quite different. I'll talk about it, why in quantum communication we do need these quantum memories. In a lot of times it comes as for synchronization and buffering of a quantum network.
Okay, I see. Thank you very much. It's really amazing when you think about it, in the sense that we know all these quantum phenomena are so delicate, and any kinds of interaction with them can destroy those quantum properties. But you're saying you have the technology to actually, to store these quantum bits of information and then retrieve them, and you're going to talk about that
Yes, I
in
mean,
your presentation. Okay, very
yeah.
nice. We wait for that. So the next concept is quantum repeater. Would you mind telling us briefly about what's a quantum repeater?
Sure, of course. I mean, I do actually have a slide, so I'll talk about it much more with graphics
Okay.
in a little while. So actually, maybe better we just wait there, because I show all the elements that a quantum repeater needs. But very, very briefly, the big problem right now we have with quantum communication is the issue of loss. Similar to digital communication, when you send photons or when you send optical pulses into optical fibers, the longer the fiber is, the more lossy your system gets. So and this loss is exponential. So a fiber that is 200 kilometers is 1,000 times lossier than a fiber that is 100 kilometers. So the moment the distance is only twice longer, your loss is 1,000 times bigger. So this is easy to solve classically. You always have these you have these classical repeaters. Every 25 kilometers or so, there is just a tiny box out there that reads the data, multiplies it, sends it back to the network. In quantum, this is impossible, because you cannot read the quantum states. The whole network, the whole concept is about not measuring or not destroying that superposition. So you cannot just simply read what the superposition is and copy it. That's impossible. So we have to go through this very sophisticated, yet to be achieved method of repeating information at a quantum level, which is now known as quantum repeating.
Okay, very nice. Okay, great. Well, you have a slide, and you're going to talk about it in more details. Thank you so much. And okay, let's for the very last question, I will ask you, what is the quantum bit error rate that you mentioned multiple times?
So in a lot of quantum bit error rate is something that comes up more in QKD, quantum key distribution, and quantum security. I will also briefly talk about this, although the focus of the topic is not cybersecurity. Quantum bit error rate means that how imperfect your system can be until you lose this security advantage that you can always know for sure if someone is trying to measure these quantum states in between a communication link. So in a quantum QKD protocol, you can always assure that Alice and Bob are sharing a secret key that has not been shared with anyone else, because laws of physics literally stops that. But in real implications, nothing is perfect. There is always noise, there is always losses and things like this. So in an imperfect system, it's always a matter of how large your error can be before you lose this claim and you cannot guarantee the security. And that number is usually known as the quantum bit error rate.
Okay, fantastic. Thank you very much. Thanks. How about we let you start your presentation, and then I will ask more questions, and I'm sure the audience will have more questions at the end.
Awesome. Okay,
so
great.
The floor is all yours, Mehdi. Thank you.
Thank you. Of course. So I'm just going to take around half an hour or so, talk a little bit about quantum communication, and more specifically what we do at Qunnect, which I call it the real world, there's a typo here, real world, not word, the real world or telecom integrated quantum communication. I'm more talking about quantum technologies that can be field deployed and can be used and integrated into the current telecom infrastructure in order to create a very quantum friendly infrastructure for transmitting photons and qubits across a network. Now, I briefly mentioned this. The whole point of quantum communication is to bring everything down to single photon level, or to a quantum level in which we can leverage from the properties of physics, such as properties of quantum, such as entanglement or superposition, in order to bring enhancements in measuring, in security, and in other aspects to to give you a few examples of why we need quantum networking, of course, quantum computing is nowadays much more famous. You can like factorize a large prime number if you have a quantum computer much faster than a digital computer. But eventually you want to be able to connect these quantum computers to each other. You want to have a distributed quantum network, let's call it the quantum internet eventually. That cannot happen digitally. You still need to be able to send your qubits through the communication networks while maintaining their properties. The other very famous application is, of course, QKD, quantum key distribution, which is a method to securely transmit a key between Alice and Bob, a secret key, and you always can guarantee one in between is listening to. It's a more simple method of replacing a mathematical algorithm with a physical approach of for security. Quantum network also has other applications to sensing and even astronomy. It can allow us to really create like telescope arrays that are very large, so they can give us like unparalleled resolution in observing the deep space, and very unparalleled sensing resolution in measuring, for example, Earth magnetic field or gravitational fields around the universe, pretty much. So it's a very important concept for us to realize. You can usually put quantum networks into 2 generations. One generation is very well established, even commercialized nowadays. It's a direct qubit transmission. So your quantum bits can directly go from Alice to Bob. There are companies now that they sell these things for point-to-point quantum encryption. They come with relatively high rates and everything, and are very, very secure for using. But the application is very limited, because if you directly send your photons, encoded photons from, let's say here, Alice to Bob, it only works to a certain distance. If I increase my fiber length beyond a distance, the loss is going to getting a lot bigger and bigger, and the more photon I lose, the harder it is for me to assure that the network is secure. So usually all the current protocols and current technologies are secure around 100 kilometers or so, let's say, depending on the protocol. But the second generation is about, hey, how can we increase this distance? As I briefly mentioned, I cannot just simply come and copy the quantum states. That's impossible, because I cannot read or know what that superposition state is. What I can do is to use quantum itself to find a way to repeat my information, or something equivalent to repeating, which is usually known as quantum entanglement networks, or a more general term of a quantum repeater, which I will talk about in the next slide. But very briefly here, entanglement is a property of quantum which allows you to have pairs of photons that are correlated with each other. And this correlation is non-local, so it doesn't matter how far away these photons are from each other. As long as they are not perturbed, you can be sure that they still save this, they still have this correlation, even if they're across the universe. And Alice and Bob can use this correlation in order to send information to each other, and in order to do instead of doing it directly from Alice and Bob, they can do it locally at each stations and share a secret key. This is something that's been done, especially like now. China is a pioneer in increasing these distances and creating these networks, even doing it satellite-based. So it's a technology that is now growing very fast, especially for the applications when it comes to quantum repeating or distribution entanglement. The concept is relatively straightforward. It says that, hey, assume that I do have now like 2 entanglement sources. Each of them are creating a pair of photons, and these sources are 100 kilometers or so apart. Is there a way I could end up with 1 pair of photons that are entangled to each other, but are 200 kilometers apart? As I said before the talk, there is a significant difference when it gets to the fiber loss between 100 and 200 kilometers. Whatever 100 kilometer loss is, 200 kilometers has 1,000 times loss here. So of course I could just send directly, start with 1 entanglement source and send the photons 200 kilometers apart from each other. But then that means that my rate is going to decrease by a factor of 1,000. What is worse is that if I increase this distance beyond 200 kilometers, it's going to drop much, much faster. even a network of 500 kilometers is 1 trillion times lossier than 100 kilometers, for example. So I cannot just simply send the photons there. What I can do is to a process that is known as entanglement distribution or entanglement swapping. So I can start with 2 pairs of entanglement that are 100 kilometers away from each other, end up with only 1 pair of entangled photons that are 200 kilometers apart, but now with a better probability than just starting with one source. The way it works is that in reality, you do need to add a lot of quantum devices in between. These are the essence of a quantum repeater. For example, I want to be able to use the telecom infrastructure. Yeah, fibers are designed for very specific wavelengths. O-band and C-band are around 1300, 1550 nanometer wavelengths, where you get the minimum loss. So if my entanglement sources are not creating photons at specifically those wavelengths, I need devices commonly known as quantum frequency converters to convert the wavelength of these photons without hurting the entanglement shared between them. So they'll be much more suitable for the telecom fibers, and assume that these fibers that I have here are each long, 50 kilometers or so apart. Now, the other problem is that now I'm going to the fibers. There are several things that happens in a telecom fiber, to mention 2 of them. First of all, not all the fibers are the same length, especially when I want to actually use the infrastructure out there. And the other problem is that the loss in the fibers are not deterministic. If this 50 kilometer fiber has a loss of, let's say, 1 to 10, out of every 10 photon, only 1 arrives at the end. I never know which one arrives, so it's always a random process. So when the photons comes from the other side, they're not coming out the way very nice and being synchronized at the beginning. They're not coming out together. They're all coming out as a different random time. So I would need to have a device, which is the quantum memories or a quantum buffer device, to bring back the synchronization, to store the photons that are arriving faster, or to store the entangled pairs that successfully arrived there, while I'm waiting for the slower photons or the next pair of entangled photons to arrive so I can synchronize. Of course, the other problem is that quantum memories may also operate at a different wavelength. So I need to be able to convert the wavelength again using frequency converters. So sometimes I may, depending on the network, I may need up to 8 different frequency converters just to make sure that the photons are always optimal for telecom fibers, for the quantum memories, and for the entanglement sources. Now, after the quantum memory successfully synchronize all these photons, there is only one step left, which is known as entanglement swapping. I can do a joint measurement on 2 of these photons to create the correlation between the 2 faraway photons that never even met or are not even from the same source. This is generally known as a Bell state measurement, named after famous scientist Bell. And its job is just simply to distribute entanglement, to swap entanglement between photons that were never from the same source. So a structure like this, although it looks very complicated, will allow me to create entanglement photons that are 200 kilometers apart from each other, starting with 2 sources that were only 100 kilometers apart. Now, this may seem over-engineering as hell to do something like this, to increase 100 kilometers or so. But the good thing about this is that this is a scalable network. Instead of 2 entanglement sources, I can have 10 entanglement sources. I can have 1,000 entanglement sources. And of course, 1,000 more quantum memories and everything in the middle. So I can eventually increase the distance from 100 kilometers to literally all across the continent, and eventually the planet Earth, wherever the fibers are going, which will be pretty much impossible to ever do without a quantum repeater. Everything you see here is one quantum repeater node. All we go through is to allow to increase the distance that the photons can travel without damaging the information or the state they're carrying, in this case, the polarization. Now, for us, we do want to do everything everything field deployable, let me put it this way. So we are developing technologies that need to go out there and work in a telecom network or a satellite network or anywhere, but it's not in a lab anymore. So there are several challenges we do need to address. Compared to quantum computing, which is usually done at very, very cold temperatures in very, very controlled environments, like a very fancy lab at IBM or Google or universities, we want to build robust quantum devices that can be reliably left out there for years, hopefully decades, without any major maintenance or anything like this. I cannot emphasize such a hard task it is. To give you just one example, what I have here is from Muquan, a company in France. This is a gravimeter using light matter interfaces. It literally took them 12 years to build this device that works reliably out there to measure gravity. And they even had to go reinvent the lasers. Literally, they had to build their own lasers because the laser technology that is out there is not even that reliable over a long period of times. We do develop everything at Qunnect at room temperature. That is one of our big advantages. It's very important to understand that you cannot have cryogenic technologies or laser-cooled technologies everywhere on the Earth. So keeping it at room temperature, although it's very painful to develop, believe me, it's very, very necessary to unlock this field of deployability. And then the other issue is that you want to be able to create or build a compatible quantum network. As I was mentioning, we have quantum frequency converters, entanglement sources, quantum memories, measuring stations, things like that. And in quantum, there are many different ways to do each of these technologies. I'll talk a few of the quantum memory ones, but they're not necessarily compatible with each other. So if you have an entanglement source and a quantum memory, your problem is not solved, because even if each of them are individually very efficient at a quantum level, nothing is guaranteeing that the connectivity between them is going to be efficient. So you may lose your scalability just because the photons that come out of the entanglement source is not compatible with what photons a quantum memory wants in terms of wavelengths, in terms of line widths, in so many different aspects. So it's very important to pick a platform that you can build all your devices around that platform with high compatibility. The other things we're going through is that we don't want to reinvent the wheels. We don't want to go out there and tell people that, hey, you have to just start over, create a new telecommunication infrastructure that is quantum friendly. We want to be able to upgrade the current infrastructure that is designed for classical optical pulses and turn it into a quantum friendly environment so photons can safely travel. It's really not easy because these fibers are designed for optical pulses, but not at single photon level. So our team is developing many different auxiliary devices to go integrate in a network, to monitor the network, to compensate for everything that the fibers and fiber hubs are doing in order to make it quantum friendly. And finally comes the part that most of your audience is probably more interested in, the software suite. It's impossible to have a quantum device that works so efficiently at a quantum level, but it's going to go out there in the middle of desert or somewhere for a decade or so. So you need to add a lot of software abilities. In our case, we use machine learning in order to develop self-aligning or self-optimizing quantum devices. And our plan is to use machine learning to create this software suite that can control the whole network. So always make sure that all the devices are in sync with one another. Now, I'm talking a little bit slowly, so if I'm getting close to the end of my time, someone please let me know. Now, I'm going to dive a little bit deeper into one of these, which is the quantum memories and in general light matter interfaces. It's a very ideal way of creating all those elements you need in between the quantum memories, the frequency converter, or even the source. You can use atoms to create the photons. You can use atoms to convert the wavelengths or to store them. As I was mentioning, there are pretty much infinite different ways of doing a quantum memory, starting from like laser-cooled atomic ensembles, or a single atom even, which is done quite often at MPQ, using crystals, NV diamonds, silicon vacancy, nitrogen vacancy, crystals using rare earth dope crystals. Most of these technologies need either cooling at cryogenic temperatures, like the silicon vacancy that only works if your temperature is below 0.5 Kelvin, or they need laser trapping and very complicated cavity systems like the single atom MPQ experiments. So these are all amazing ideas for making a quantum memory, but they're not all ideal for deployed fields for a technology that is going to be commercialized and go out there, because first of all, they're either very, very expensive, and they are very, very hard to maintain and really need to be always with scientists and stuff. So the option that we are very focused on, been done at Oxford, Stony Brook University, where I did my PhD, and now in Qunnect we are commercializing it, is using room temperature and samples of atoms in a vapor cell to store photons. It's very noisy. It's taking us forever to get rid of the noise and everything, but we have successfully shown that it's possible to have a quantum performance at room temperature that can store the photons for a longer storage time with good fidelities, with high fidelities, which can be very useful. And now we are in the process of modularizing it and create portable versions that can work outside. To talk a little bit about this, but without really diving deep into it, our quantum memories work based on a concept known in physics as electromagnetically induced transparency. EIT says that, hey, let's grab some atoms. We always use rubidium-87 in our case. You can have two ground states, B and C here, and an excited state A. Yeah. If my photons, if my qubits are coming with the energy E, so they are exactly on resonance with the transition B to A, if I send them to the vapor cell, they're going to get absorbed because the photons, the atoms are going to absorb this. Yeah. But under very certain conditions, I can apply a strong laser field that is tuned to AC, so to create this lambda structure, which will modify the medium in a way these photons will not get absorbed. So it's going to force the medium to be transparent to my original photons. And now I can use this control field that I'm showing here with omega to control the transparency of the medium for my photon, which will allow me to store them by making the medium fully dark, or retrieve them and let them pass by making the medium fully transparent. So at a single photon level, experiments usually look like this. The dotted line here, this is a pulse with only one photon on average in each pulse. The blue part under it is the part that we couldn't store because the efficiency is not unitary. The efficiency is not 100%. And then the light green is the background noise, which is due to the control field. So you can see that I had the light on, I had the pulse, I had the control field on. The moment the pulse entered the medium, I turned off the control field. I forced the medium to store my pulse. And then after a certain time, in this time very short, after 1 microsecond or so, I retrieved it. You can see that peak. So that peak that is retrieved is a portion of my photon in this experiment with only 5% efficiency that's been successfully stored in a room temperature quantum memory for extended amount of time, for 1 microsecond. What makes this a quantum memory is that how well this 5% is maintaining the polarization, because this memory is designed not only for storing a single photon, but also the polarization I'm encoding on. And this 5% is maintaining the polarization with about 95% fidelity. So it's very, very good in maintaining the quantum properties of the photons, which makes it a quantum memory. Since then, since the time of this plot, we have a lot of progresses. For example, when it gets to the storage time, now we can increase this storage times to beyond 100 microseconds or so. So we store pulses with high efficiencies, now 50% or so instead of 5%, for longer storage times, which is done through a lot of engineering. And this is the part I was talking about, that regardless of what polarization I send in, the 6 main polarizations, I can get that exact polarization out, but with a reduced, of course, probability at 90% or so, which is one of the things we're also now working on to increase. Now, this is really a hard challenge because we did start with like tabletop optical experiments. That's the one you see up there at Stony Brook University during my PhD. So there is this huge table filled with equipment, especially the filtering systems, because now you're working at room temperature. So the biggest enemy you have is all the filtering noise that you have to be able to get rid of without destroying that one good photon that you care about. And the ratio is 10 to the power of 12 ugly photons for each good photon. But After we figured out, after we found out how to make this work efficiently and with high fidelity, now it's much easier to move towards portability, to make it smaller. We did some experiments with KTH in which we made a very basic portable version of the memory, shipped it to Stockholm, and they could successfully use in a hybrid network with quantum dot photon sources. And since then, moving towards the Qunnect work, we have started creating the rack mount version. What you see under here, Mark 5 is the one that we're working on. This is a very, very robust technology. This is a device that can maintain the optimal performance of the quantum memory for a very long amount of time. The tabletop ones were only stable for like 10-15 minutes because they're very sensitive to the temperature. The new versions we're building here are capable of stabilizing the temperature 1 out of hundreds of thousands of a degree. So they're much, much more robust in terms of managing mechanical and thermal stabilities. And of course, our eventual path is to move towards a miniaturization version. In this case, by miniaturize, we mean like this prototype is 8 by 6 inches, so it's not tiny. But for communication, we're really not looking for on-chip things. As long as it's in this size, we're of course more than happy. I may skip through this a little bit faster because time is passing quickly. So we've done a lot of experiments in quantum networking because, as I said, it's not just about having a good quantum device, in this case quantum memory, but it's also a matter of how compatible this device is in a quantum network, even with the other quantum memories. Yeah. So we did experiments in which we created random photonic states in a different lab using 2 different setups. Each of these photons would go to 2 different quantum memories, and we would store the photons, and after storing them, we would do an experiment like an HOM fundamental measurement, which is very similar to what you need for swapping entanglement. To just briefly talk about the results and why something like this matters, is all about that synchronization issue. Yeah, in this one, the plus on the left side, the original photons at Alice and Bob are not generated at the same time. So if I send them to this HOM measuring device, you won't see any interferences because they're not overlapped. And all these devices, HOM, ballistic measuring, they're very, very sensitive about the temporal overlap of your photons. They need the photons to arrive simultaneously if you want to do a 2-photon interference experiment. But we sent each of them to 2 different quantum memories. The quantum memories allow us to synchronize them because we can store them at different times and retrieve them together. So we can achieve plots that you can see on the right side, that we can see a decent visibility at single photon level for our photons that were not originally synchronized, but the quantum memories allowed us to synchronize. And it actually proved that the quantum memories are capable of creating indistinguishable photons with very, very high fidelities, 99% plus, which is a very, very key factor for any quantum to manage to keep the indistinguishability of your particles. Now, these ones I'm also going to briefly mention because it's not just enough to have quantum memories, you need to have the whole product suite. But one of the good things about rubidium is that it also has transitions at telecom. For example, some of the transitions I have here are around 1310, 1320, 1360 transitions. So I can use them to convert my photons. Quantum memory works at 795 nanometers, so it's not ideal for a telecom network. But I can convert these photons into, for example, 1367 and vice versa. People have done these experiments, and this is one of the devices that now we are developing at Qunnect also to create these quantum frequency converters. A big advantage is that we are using the same atoms, so they're very compatible with the quantum memories. We are even now developing photonic sources that can use the atoms. So everything will be very compatible, everything rubidium-based at room temperature with very high quantum connectivity. This is just a few of the other products we're building. I still have the frequency conversion here to mention. One thing is that another auxiliary device you need when your network gets complicated is that all these devices work using lasers. A converter needs a quantum repeater, as I showed you up there, for example, needs around 28 different laser modules across the network. And these are all need to be very precisely locked to atomic transitions or very precisely locked to each other, very stable in terms of their frequency. So we are also building in-house locking systems that allows us to lock several different lasers together. So in a fiber hub or so, when we go with quantum memory sources, converters, we can only have one of these devices and lock all the lasers to corresponding systems. I talked a little bit about the auxiliary things that we are building to make these more suitable for network implications or using for deployed networks. One of these is right now we're working on is in a machine learning algorithm that allows us to self-optimize the filtering cavities in the quantum memories. Those are the most sensitive elements in the quantum memories that are very, very sensitive to optical alignment of the incoming photons and also to the temperature in this case, because we're using passive echelon cavities. So now we're developing this software that can automatically monitor the system during the downside and using reinforcement learning to adjust the mirrors, adjust the temperature to make sure the cavities are always optimized. We are also using a very similar protocols for correcting the polarization rotation that happens using the fibers. As I mentioned, these fibers are not designed for preserving this like quantum information, so they're gonna start rotating and damaging these polarizations. But I can have a system in which is continuously during the downtime of my network is testing the rotation in the fibers and is continuously compensating for it in real time. And of course, for us, one very important thing is to be able to do the field testings. If I'm not going to stop talking about field deployable technologies, we also need to actually deploy them in a field to make sure they do work. And most of the experiments you've seen so far done by different scientists is using fiber pools in a lab. So the long distance was not an actual fiber. Here we want to do experiments using the actual telecom fibers that are buried in New York State. So right now we have collaborations with the Stony Brook University and Brookhaven National Lab to use their infrastructure or the fiber link that connects these two with each other. It's a link of 68 kilometers to create a very hybrid modular quantum networks. And of course, our eventual goal is that it's going to take us a while, but also with partnering with the Air Force Research Lab to create a network that is across New York State, all the way from upstate to New York City, where Qunnect is, to the end of Long Island, where Stony Brook and Brookhaven National Lab are. Doing this field testing, I know the technologies are still premature for actual integration and creating an efficient quantum network, especially for this distance. New York State is a very big state, but this is a very critical step for us to really develop a product suite that is compatible with the infrastructure, rather than us assuming that it's going to be compatible. So by doing this field testing, we're going to learn quite a lot about everything we need to develop and everything we need to change about our devices to create maximum scalability, maximum efficiency when we integrate into these networks. I probably jump over this. The only reason I have this here, I want to mention that, let's be clear, these technologies are very, very early stage, even when it gets to commercialization. Even when we're talking about a modest market size of 8 billion, we're talking about 2028. We're not talking about tomorrow or next year, but where we are right now is a very interesting stage. So what we do at Qunnect is really as deep tech as it gets. We really don't care that much about the revenue. We really care about building this product suite, building the IP and the technology and the protocols that can be used eventually in very, very large scales. So we are in a stage that we get to define which technology can be the key technology. We get to define the protocols that we eventually use. By we, I don't mean specifically Qunnect, of course, the whole community that is working on the quantum communication. And then hopefully in 8 to even like 20 years from now, we get to a point that we have all these technologies deployed and we have these quantum networks at their full power. Just quickly, now we get into the final slides. I think I really stick to the half an hour, I hope. Yeah, so of course our team is expanding and I'm very, very thankful. Everything you're seeing here is happening with a large team at Qunnect and a larger team of collaborators at Stony Brook and Brookhaven National Labs. So this is our team. Several new scientists recently joined us. We always have room for more people. If you guys are interested to join, please let us know. I know that most of the audience here are more on the machine learning side, but we do, as I mentioned, are expanding everything we do for creating machine learning enhanced quantum devices. So there are very interesting opportunities. We actually now have a senior scientist for machine learning also. And that's it. I just want to thank everyone here. I just want to mention that this is a very, as I mentioned, it's a very interesting opportunity. The technology is getting to a point that we can realistically talk about something as complicated as a full deployable quantum network. And there are so many different approaches and so many potential for research and collaborations. It's very, very important for Qunnect to create an environment in which everyone can collaborate together, everyone can work together in order for a better good to create a better communication network. I should thank our funding agencies. Everything you saw here is coming from Department of Energy, Air Force, NSF, and our private investors like Quantum Ocean and Accelerate New York and the other private investors. And by this, I'm going to leave everything back to Reza for more questions.
Thank you very much, Mehdi. Thank you for telling us about all the great stuff you guys are doing. It's really, really, really impressive as someone who's been into this on the commercial side for 3 years. It's really amazing to see companies like you guys are making products that are, focused on being field deployable, being practical in real life conditions. Because as we know, all these technologies are at very, very early stage, and right now it's just still mostly in labs and under very specialized circumstances, like millikelvin temperature, which of course always is very hard to achieve, and it's very, very expensive. So it's amazing to see you guys are focused on the real life applications of this, and to see you are developing several products that can basically facilitate getting to the point of having a real life quantum network. Thank you so much, Mehdi. I checked to see how many questions we have. We have several questions. I will start with, okay, Amir is cheering for Orca Computing.
Orca, yeah. I'm a big fan.
I assume he has some links there. I love Orca as well. I know those guys. I wish them all.
They were the Oxford people that I was referencing in that slide. So yeah, Orca is a spin-off from Ion Bombs, this group now led by Joshua Nunn. It's a very, very similar technology that they're doing. They're using cesium atoms, but the basic is very the same. The big difference is that they can leverage excited states to get rid of the noise, but with the cost of very short storage times. But that's very suitable for computing anyway, so they can store for like several nanoseconds. For us, it really matters to store long enough to synchronize a network, so we have to use the ground state. So for us, there is no way to easily bypass the noise. So we have a noisier system, but with longer storage time. But the good thing about each of us is that we know where our device belongs, in quantum and in computing and communication.
Okay, fantastic. I will ask you more questions about it. I think now they have a lawsuit on their hand now. Amir mentioned that's based on his patent, or he's one of the people there. Okay, good to know. We will discuss those later.
Yes, please.
Yeah, Javier mentioned, what is the minimum cost estimate for developing a rack or a box module to give satellites like those launched by SpaceX quantum communication capabilities?
Oh yeah, that's going to be expensive for satellite, yeah. Well, I mean, I don't know how to break this down because the satellite part and everything. So the device itself is going to be expensive, but not insane, because you only put one or two in a satellite anyway. So you can get that done with 10, 20 million and you're good. But obviously the satellite itself, you need a couple of billions for that. The Chinese version, I think, cost them around 2 billions for the satellite that has an entanglement source in it. So the more expensive part is the satellite itself. For fiber-based technologies, these devices are gonna, at this stage, are relatively expensive. The quantum memories we build, all these things, even for us, it really cost us. But that's mainly because it's not, we're not mass producing. We're literally building things in hand and using a lot of times in these cases at the research grade level off the shelf elements. So even the device for us is very expensive. But if ever this goes to a path that you want to build these quantum memories in a larger scale, you can reduce the cost to definitely less than 10K or so per quantum memory.
Okay, fantastic. That's for these kinds of device, basically fiber-based, not the satellite one.
For the satellite ones, it's also, of course, it's more expensive to develop the device because you need a space-compatible device. But then you don't even need that many of them because these fiber-based ones, you need thousands and thousands of quantum memories. But for satellite ones, you literally need one entanglement source, for example, in a satellite. So the device itself is not going to be the main cost. The fact that you have to send the satellite up is going to be the expensive part.
Of course, that's always cost. There are lots of costs associated with that. Thank you so much. I do apologize if I'm reading these names not exactly correct. Deagle Boy asked, okay, how soon can this technology be miniaturized down to the atomic level, individual atom quantum states, instead of at the photonic level, to store quantum states at room temperature?
I don't know if I exactly follow.
Yeah, I'm not exactly sure either. Is it talking about, okay, the whole device to become atomic scale, or using those other technologies instead of that? But there's a question, there's a follow-up question from him or her. Is network timing extremely critical to this solution, and what are the tolerance for frequency stability to encode and decode quantum photon states?
I can answer this better. Yeah, the timing is very important. That's actually one of the devices I didn't mention here. We're building a synchronization device that allows us to synchronize our pulses that we use, like for the lasers and these things that result in generating the photons or for storing the things across the network. So our device is capable of doing it around like in the range of 100 picosecond or so. We can synchronize the network, so we can synchronize remote quantum memories from sources and stuff like this in sub-nanosecond times using White Rabbit and GPS combined. So that part is definitely important, and it's one of the devices we're developing. I didn't talk about it because it's a more less quantum-y device, but very necessary for the network. The second part was, the laser stability. We do need stabilities of usually sub megahertz. So a lot of things are locked to or very close to megahertz for these memories to work. That's also one of the disadvantages we have, for example, compared to ORCA. So for us, we use saturation spectroscopy for locking the lasers to specific atomic transitions, or like phase locking them to each other, which is very, very precise. So anything megahertz or less would do the job for us.
Okay, thank you so much for the explanation. If I ask, if you ask the question number one more clear, we are happy to get back to it. But for now, Mehdi, where are the state of the arts? You mentioned some values for the timing that you can store, right? But where are you standing in comparing to other technologies? Is there other technologies that people are using to build these quantum memories? And what are the state of the art technology world right now?
So when it gets to the research lab, or a research level, using room temperature quantum memories is not the smartest idea to do, because, for example, you can do cold atoms if you laser trap them using magneto-optical traps. If you fix them in very specific places, you can significantly reduce your noise and increase the coherence time and everything. So you can have a memory in a cold trap system that has very high efficiency, very reasonable efficiency, very, very high fidelities. People have done it with like single atoms with like 99.9% fidelity, they are around like 91%. It's a very, very big difference. And you can do it with long storage time, several milliseconds or so. So of course, quantum works much better at cold temperatures. So the more you make it cold, the easier it is to maintain the quantum properties. Yeah. The big problem is that those devices are very, very complicated usually. And they're really, really not a good option for a scalable field deployable technology. The moment you're talking about field deployable, you kind of have to say bye to cryostats or like even laser cooling, because it's very complicated to manage the stability of these devices when you're talking about thousands of devices eventually in a network. So first of all, we're kind of stuck with room temperature, but also on a more beautiful side is that I truly believe eventually there is nothing that is forcing quantum to only work at cold temperatures. At cold temperatures, it's just easier to maintain the quantum coherence, to just freeze atoms in a certain place so they don't collide or anything like this. But now scientists are learning how to create quantum coherence at room temperature. Our quantum memories, there are millions and billions of atoms together coherently storing this one photon for the time. It's a noisy environment. Everything is moving. There is Doppler broadening. These atoms are diffusing very, very fast. But we can manage to create this one coherence between atoms that allows us to store these photons, because this is a coherent process. When we retrieve the photon exactly has the same temporal shape. The photon has the same frequency characteristics and the same polarization. So it's not like it got absorbed and restored.
Is there any other technology that can be used for room temperature?
At room temperature nowadays, I've seen people doing some nice progresses with the NV centers. Chicago people, are doing nice stuff. I really don't know what is their latest results.
I'm assuming David Ashlam's group, right?
Yes,
Okay.
they're trying to do this. Of course, that's good, because we can make it smaller than what we can do, because we're always limited to a vapor cell and magnetic shielding and stuff like this. Of course, yeah, it's doable with those two, apparently, as it seems like, but not that quickly. And also the other issue is that rubidium is a good device for a network, because it has all the transitions you need to create entanglement sources, to create frequency conversions, to operate at telecom wavelengths, things like that, to even connect to experiments being done with members of our team to connect the rubidium systems to ion for quantum computing, things like that. So rubidium is really, really an ideal platform for creating an all-in-one quantum ecosystem.
Fantastic. Okay, so those layers that you showed in your graphs, those are magnetic shields, and perhaps
I think so, yes.
Okay, very nice.
Sorry, it's a little bit slow by the time I get there.
Yeah. Actually, about this slide, we can come back to it later. Seems like you guys are working right, exactly. This is what I was talking about. You have several layers, that seems.
Yeah, these are the mu shieldings, mu shieldings.
Okay, fantastic. And yeah, so your main products right now, what you're working on, the two biggest challenge that seems that you are dealing with is storing the quantum information. And on the other hand is the quantum transduction, and how to be compatible with whatever, classical networks and fiber optics, infrastructure that we have, right?
Yes, that's pretty much it, yeah.
And for both products, seems like you're using kind of the same technology, rubidium cells, to solve the both.
So the memory is much more advanced. Yeah, the memory is something I've been working on for like 8 years now or so, 7 years or so. So it's actually in a point that the performance is good enough that the R&D is, let's say, still 50% research to bring every parameters to above 98%, 99%, but 50% also engineering to make it very robust for deployed networks. But the thing is that we have started with this. One of the reasons was because 5 years ago or so, people have already figured out entanglement sources using parametric down conversion in crystals. People had done like experiments in networks and stuff like this. The only part that was actually missing for a quantum memory, for a quantum repeater, was a quantum memory to synchronize a network. Otherwise, you still lose, your loss is the same rate pretty much, especially in the larger scales. Now, then we build the quantum memories. We realize that, okay, now we have a quantum memory, but it's not necessarily as compatible with the current, like parametric down conversion creates photons that are 100 gigahertz wide line width-wise. We want something that is 2 megahertz, for example, or very close in the megahertz range. So we realized that, okay, maybe now we go build our own entanglement sources also. So these are the things that in our company is much more on a research scale right now. And then when we figure it out, we're hoping that our experience in making portable quantum memories can come very handy to quickly make portable version of all those devices as well.
Fantastic. Fantastic. Okay, I really, really wish you all the best. Let's see if there are other questions. Okay, there are. From Diggle Boy, question is, can vacuum chambers be used to store the photons instead of cryogenic chambers to lower the cost and reduce the noise?
Yes and no, depends. So for example, the one that I was talking about, that you can make a quantum memory using the same atoms, but trapped in a magneto-optical trap, you do need vacuum. But the cooling is not coming from a cryogenic system, the cooling comes from a laser trap system. So you can use, so it needs a vacuum system and extra lasers to do this. But even that system is still going to be much more expensive than what we build and much less stable when it leaves a lab. There are actually companies in the US like Cold Quanta that builds miniaturized traps like this. And we had one of them in our previous lab and worked with. These are very, very awesome technologies, but they are not really cheap and scalable in this sense. Vacuum, but you cannot always escape the cryogenic, like the silicon vacancy quantum memories that people build in Harvard, MIT. You have to cool them down in a deal fridge. It's not, the vacuum is not going to cut. Of course, it's in vacuum too, but you have to bring them down using liquid helium.
Okay. Great, thank you so much. Mehdi, I will ask you this as the one last final question, and I'll let you get back to building all the great products and the quantum
there's no rush.
internet that you are creating right now. The question is, cesium timing devices are used for terrestrial and satellite networks. Can this also be used to generate photons as a hybrid device to lower cost in both environments?
Sure, cesium is very similar to rubidium. Yeah, these are all alkaline atoms. The reason they're useful is that they only have one electron in the outer shell, so they kind of behave like a large hydrogen atom because it's like only one atom far away, one electron far away, and it's cesium is what like Orca quantum computing. There are atomic clocks with rubidium atom also. They are the ones we use for timing, for example, synchronization. So both cesium and rubidium are very close. There are a little bit differences when it gets to the noise and stuff like this. So there are some very technical reasons why we use rubidium, not cesium. But it's not going to reduce the cost because it's literally like the same exact thing that I'm building, just replace the rubidium cell and put a cesium cell and use 2 different lasers, and it's going to work.
Okay.
So yeah.
So it won't make a huge difference in that regard. Okay. Thank you so much, Mehdi. Thank you for being here. Thank you for sharing all your great knowledge and experience in this field with us and with our audience. And thank you, everyone, for being here today, perhaps on your lunchtime if you're on EST time zone. We really appreciate you being here. Please stay tuned. We will have other talks just like this one. And the next one will be Professor Roger Melko. He's an expert in quantum machine learning. And I bet you will love that talk from Perimeter Institute and University of Waterloo. It will be held next month. More information about that will be released soon. Thank you for joining us today, and I wish you all the best. Thank you, Mehdi, and
of course, thank you guys. You too. Take care, everyone.
Bye, everyone.